Hello guys, welcome back to my channel. And this is going to be a really short video because we're going to be doing an infinite sum involving the Riemann Zeta function. So let's get to it. So basically we have our sum, infinite sum, let's call it y. We have the sum from n equals 2 to infinity of the Riemann Zeta of n divided by 2 to the nth power. Now the interesting thing to note here that inside the Riemann zeta function, the argument is in terms of the index of the sum, right? So we definitely can't take it outside the sum sign because you know there is an n term, right? We can't just change the meaning of the entire thing like that. So what I'm going to do is because we can't even do anything with the denominator. So what I'm going to do is I'm going to write Riemann zeta function in terms of uh, an infinite series, which is basically its original definition. So inside this infinite sum, I'm going to have another infinite sum, but this time we have an index m equals 1 to infinity. And then what's the Riemann zeta function? Well, it's this index m to the nth power, right? And that's being multiplied with 1 over 2 to the nth power. Now, the only thing that we can do here is to assume uniform convergence. And you ask me why, I'll tell you. Because that's when we can interchange these two infinite sums. I mean, as I explained in a previous video, we have to check for the dominant convergence theorem or Fubini-Tonelli. I mean, it depends, and it's quite beyond the scope of my knowledge and the scope of this video. So let's just assume uniform convergence and change the order of these sums. So outside we'll have sum from m equals 1 to infinity, and then inside we have the sum n equals 2 to infinity. Well, let's just uh, since everything is raised to the nth power, why don't we write multiply everything together and then raise it entirely to the nth power. And now by the looks of this thing, we have well, let's just write it out. Let's It will be easier to observe stuff like that. So when n is 2, we have 1 over 2m, the whole thing squared, which is nothing but 1 over 4m squared. And then when n is 3, we have 1 over 8m cubed, right? And basically you're adding successive terms because it's an infinite sum. It's a sum essentially. So it's going to be something like 1 over 4m squared plus 1 over 8m cubed plus 1 over, when say n is 4, 2 to the 4th power 16 times m to the 4th power, and then 1 remains unchanged, 1 to the nth power is just 1. This goes on till infinity. Well, by the looks of this thing, this looks like a geometric series, right? It's a geometric series because you have the first term, we commonly denote that as a. We have the first term as 1 upon 4m squared, and the common ratio, when you divide successive terms, you just obtain 1 over 2 to the m as the common ratio. And well, we can certainly check for convergence now. What was the condition for convergence of a geometric series? Well, we have to check whether the common ratio, the absolute value of the common ratio, is less than 1. And what was the common ratio here? 1 upon 2m, absolute value of that. Well, is that less than 1? Well, let's see. M traditionally, by our definition, when we introduced that as an index, goes from 1 to infinity. So the least value m can take is 1. So when m is 1, when m is 1, the ratio is 1 over 2, which is definitely less than half. And then as m increases, the denominator gets bigger, and this entire fraction, this entirely is always less than 1, right? Because if the denominator is getting bigger, the entire fraction is getting lesser and lesser and lesser. So is this thing holds true on this interval where m belongs to open to infinity. I'm sorry, 1, because m initially starts with 1, right? So basically our um, absolute value of the ratio is less than 1. So our geometric series converges, and the sum of series, we can apply this formula now directly, is a over 1 minus r. So what's a? It's the first term, right? 1 over 4m squared divided by 1 minus 1 over 2m. Well, now instead of this thing over here, instead of this thing, we can directly substitute this to be the sum of the geometric series. That's what we are calculating here, the sum of the geometric series. Well, if when we actually calculate this, we have 1 over 4m squared divided by 2m minus 1, and then this 2m goes in the numerator. So 1 2 cancels out, 1 m cancels out, and eventually all we are left with is 1 over 2m times 2m minus 1. So as I said before, we had the sum from m equals 1 to infinity, and the sum from n equals 2 to infinity of 1 over 2m, the whole thing raised to nth power, and we just calculate this inner term, right? So let's just plug that whatever we calculated last time through the infinite geometric series formula. We calculated 2m times 2m minus 1. Well, what can we do here? Well, we can do one thing. We can use a partial fraction decomposition, and the way we do that is, let me just use another page. It will be much better. And the way we do that is, let's just forget the infinite sum part. Let's just be concerned about the fraction now. So we have 1 over 2m times 2m minus 1. Well, we want to split this in terms of a over 2m and b over 2m minus 1. Since, see, the denominator has a degree 1, right? M is to the first power in both cases. The numerator will have a 1 degree less than the denominator. So if this is 1, on top we'll have m to the 0th power, right? M to the 0th power is 1. Same thing over here. Because if we had, say for example, 2m squared, then we would have to construct like a linear term on top we'll probably have to do something like am plus another constant, say c or something, if there was a 2m squared in the denominator, but we don't, right? So m to the 0th power 1, just write an a constant. Now, well, why don't we just cross multiply in this case? We'll have a times 2m minus 1 plus b times 2m, all divided by 2m times 2m minus 1. We can just ignore the denominator for now. Essentially, we have 1 equals a times 2m minus 1 plus b times 2m, right? Well, we actually need to solve for a and b, right? We need to find those coefficients that will enable us to split um, this fraction into these two sums. And the way to do that is, let's just use the Heaviside technique. So what we do in this technique is we plug in such a value of m such that one of these factors goes to 0, and there are two of these, right? There is a 2m minus 1 and there's a 2m, right? So first let's just take a value of m such that when we plug that in, this 2m minus 1 will just go to 0. So let m equal half, and you will see in a minute why. So 1 just remains 1. This is case 1. And you have a times 2 into half minus 1 plus b times 2 into half. Well, 1 is equal to a times, you have a 1 here, and 1 minus 1 is 0, and 2 times half is 1, so b times 1. Well, a times 0 goes to 0, so this implies that b is equal to 1. Well, great, we found a value of b. Well, for case 1 we chose a value of m such that this term that's being multiplied with the a disappeared, right? So for case 2 we do a similar approach, but we want to get rid of this term that's being multiplied with the b. So we let m equals 0, because when we plug in m 0, that's when 2 times 0 is 0, and then b times 0 is 0, so this term will just disappear. So let's do that. We have 1 times 1 is equal to, sorry, and then we had a 2m minus 1 if I'm not wrong. So 2 times 0 minus 1 plus b times 2 into 0. It's multiplied, yes. So 1 is equal to 2 into 0 is 0. We have a negative 1, and then this thing will just go to 0, right? So this implies that a is equal to negative 1. Isn't that excellent? So whatever our original term was, now we can write in terms of two separate factors, you can see. We had 2m times 2m minus 1. Now you can write that as, wait, let me write the positive first, always. 1 over 2m minus 1 minus 1 over 2m. Well, great, we performed partial fraction decomposition, and we obtained this nice separation of terms. Let's implement this in our infinite series now. Well, we obtained this. I mean, like the inside part, we can rewrite that, keeping the outside sum same. We have 1 over 2m minus 1 minus 1 over 2m. Well, the sum is running on all of this. Now let's just see what this sum looks like. So when m is 1, you have 2 times 1 minus 1, which is 1, minus when m is 1, this thing is half, and then plus, well, this is one pair. And then when m is 2, you have 2 2s are 4, minus 1 is a 3, and you have a 4 here, minus 1 by 4. And you can have all these pairs till infinity, right? Now, great thing to notice, if you just remove these brackets which are not that necessary, 1 minus 1 by 2 plus 1 by 3 minus 1 by 4 plus whatever till infinity. We can write a general sum for this. We can express this as a general sum. Let's use k now. K equals 1 to infinity, negative 1 to the k plus 1 power, because we want the negative to start, the negative sign to start from the second term, right? So when k is 1, we'll have 2 here on top, and negative 1 squared is positive 1. That's why we have a positive 1 here. And then when k is 2, you have negative 1 to the third power, which will result in negative 1. We have a negative here, so we want the negative on alternate terms starting from the second term. So k plus 1 divided by k, because when say k is 1, it was 1 over 1, right? I didn't write the fraction. And then when k is 2, there's a denominator 2, so k. And then when 1 is just staying 1 in the numerator, right? I mean, whatever you do with this is just staying the same. But what does this remind us of? Well, what if let's take a step back. Let's take a step back. Let's take a step back. What does this remind us of? Let me just write another expression over here. Minus 1 to the k plus 1 over k. Instead of this 1, let me just write an x. I mean, it does us no harm, because I'm just defining another expression. But what was this equal to? If you clearly remember from most of the videos that I've done about these infinite series or stuff involving Taylor polynomials, this was the Taylor expansion of the natural log of 1 plus x. Well, instead of this x, now we just have a 1. So why don't we make that substitution? So let x equal 1. So we'll definitely have the sum from k equals 1 to infinity minus 1 to the k plus 1th power over k. 1 to the k is equal to, instead of this x, I'm just putting a 1. So 1 plus 1, which results in a natural log of 2. So to reiterate, this thing is exactly the same as this thing now, isn't it? So we obtain a natural log of 2 for this alternating harmonic series, and it's a pretty standard result. Although this series is a conditionally convergent, but it serves our purpose for this problem. So let me officially write down what the solution is. Well, we had the sum from n equals 2 to infinity of the Riemann Zeta of n divided by 2 to the nth power. And what does that result in? the natural log of 2. I mean, who would have guessed this? It's just fascinating. You would think that the Riemann zeta function, when you are, taking it inside an infinite sum like this, it would definitely diverge. But no, it because when you take its take the quotient of the Riemann zeta of n and 2 to the nth power, and then run the infinite sum from 2 to infinity, you just get this beautiful result. Math never ceases to surprise us. So I hope you like this video, guys. Please like, share, and subscribe. You can reach me in the comment section if you have any doubts, any problems. Have a great day. Peace out.